We will be using freely this kind of Trotter-Suzuki formula. So if A doesn't commute with B, so the commutator is not equal to 0, then we cannot just split with like for regular exponentials. We have to use the Trotter-Suzuki formula. So in the Trotter-Suzuki formula, we have something that is scaling, becoming infinite, and then the time for the evolution that we had with A plus B, we subdivide into small intervals and we interlace A, B, A, B, A, B, and so on. Yeah, this is the Trotter-Suzuki formula. And in previous sessions, we proved that this as an approximation for finite n has this kind of convergence rate. So 1 over n scaling quadratically in time, but the constant in front of that depends on the commutation properties of those matrices. So that's maybe some useful stuff. That's a bit of a recap. Okay, so this Trotter-Suzuki formula is quite useful, and today we will be using this for time-dependent Hamiltonians. Okay, so let's see. I will just scroll through a little bit more. Okay, I won't be recapping the previous tutorial. And today I will just more or less start from scratch, and we will just use the Trotter-Suzuki formula the way we need it. Okay, so what's the problem that we are dealing with? We have our Hamiltonian. That's a Hermitian. So Hamiltonian is self-adjoint, or this is just the standard notation for transpose and conjugate, and we will have this being a D by D matrix. Okay, if it's Hermitian, then exponentiating that with some affine parameter here, which is playing the role of time if we consider quantum systems, that will give us a unitary matrix. Okay, so this kind of matrix UT will be unitary. Okay, maybe I will write it that way. This is actually nice. So the inverse of this one is just the Hermitian conjugate of this matrix. Easy to check, a good exercise if you want to consider some calculation. So, okay. Now, what happens if I have a mapping of some time interval, let's say 0 to 1, it can be whatever interval, and I have a mapping to those Hermitian matrices on our D-dimensional matrices here. And basically, I will have H with a dot here, which means that if I take any time in this interval, then I will get HT, which be just some time dependent. That's why we just define this time dependent Hamiltonian. Okay, so I get a function. I get a function of one parameter, the evolution duration, or maybe the geodesic float duration on our unitary manifold. And then I get this continuous family of Hermitian matrices. So basically what we have is that instead of having this single Hamiltonian fixed for all times and directly generating an evolution, our generator, kind of the forces in the system are changing as we go. Okay. If there's any questions, let me check in chat. I don't see any questions so far. Okay. This is kind of important because we will also want, for example, often it's nice to say that, for example, the derivative of H in our operator norm, that this is bounded by some constant. Let me use H prime, for example, and HT. HT should be bounded by some constant H, for example, for all T 0, 1. Okay, so sometimes we would ask for those kind of regular conditions. Okay. Okay, so we just mentioned the Trotter-Suzuki formula, and that will come in handy. But let me give you an example of such a time-dependent Hamiltonian. So let me consider A, B are again Hermitian matrices. And then I can consider HT to be A plus cosinus omega t B. Not a big problem, okay? In physics, we would, for example, consider a driven magnetic field, or yeah, in general, maybe some time-dependent magnetic fields would be an example. We were doing the quantum engineer's guide last week, and the motivation there was that if we have a qubit, so the box is the Josephson junction, we have some capacitor, and then we have some capacitive coupling to a time-dependent voltage source, right? Then those voltage sources are kind of giving us a time-dependent frequency, and then we get a time-dependent term. So that's connecting that way, okay? But today we are considering just a mathematical problem. For example, if I'm considering the Schrödinger equation, so I will use the minus IDT notation here, and I have some wave function or some solution to the Schrödinger equation with this time-dependent generator here, HT. Okay, so by theorems in ordinary differential equations, we know that the solution exists, and we would like to find a unitary transformation that takes our initial state and gives us all the states for all the times that we are interested in, right? So then you can ask UT, what is that? Okay, and the answer will come from Trotter-Suzuki decomposition. So now let's think how to do it in a smart way. So we will again have n going to infinity. So for example, if I would have my cosine, I would chop this interval into small pieces, and I would consider a piecewise constant sequence of those values of this cosine here. And in this interval of size delta t, which is total duration of the evolution divided by our n, then in this duration, I would have my Hamiltonian h of, for example, delta t, if I consider the Hamiltonian here. So something like this. Here I would take Hamiltonian h delta t times 2. And here I would have h n times delta t, which is equal to h t, right? Because delta t is just the total duration by I switched here the notation, so it should be actually with the sub index. So it should be sub delta t and h2 delta t, and then h t is equals to h n delta t, right? So basically, I take my my multidimensional function ht, and I query this function at a equidistant discretization of our time interval, in this case 0, 1, but you can just change units. So this is a standard interval 0 until 1. And then I just say I get a different type of evolution. So I will fill in this limit in a moment. I will motivate why this works. So I will consider a different type of evolution. Psi t is solving the Schrödinger equation, where I have a piecewise constant Hamiltonian. So how to, maybe I will call it k of time, kt, psi delta t, and k of t is something like, how to say, basically for all those times for t in 0 and 1, kt is telling me which kind of interval I'm in. So kt will be of the form k times delta t. And this k we need to figure out by considering the evolution time. So maybe this is confusing because, yeah, so this t could be some t prime or something like this. So this is in principle the full evolution time, but I can consider a different propagation of the wave function, choosing similar Hamiltonians, but really taking those piecewise evolutions, okay? And in this case, we are just composing regular Schrödinger evolutions. So I can write down what is psi t. I will use this notation u tilde hat here. Psi of 0, which we say is exactly the same as psi of 0. Okay. So the initial condition matches, and then we don't continuously change the generator. We make kicks. So in this case, U1, the final propagation tilde, is the concatenation of our delta t will in this case be 1 divided by n. Okay, and n is implicit in this kind of function, which is checking, subdividing the full interval into delta t. So I could put t here, but let's do the final evolution because then the discretization works more naturally. Okay, and then I have I minus delta t h of h sub 0 times, okay, I will need to invert this, but this will be fine. E minus I 2, no, sorry. The duration of the interval is always delta t, so not to here, I got ahead of myself. Just cleaning up here, okay. E minus I delta t again, so the same duration, but with a different Hamiltonian, h 1 times delta t, so I will just write delta t, and then minus I delta t, same duration, but a different Hamiltonian, the one evaluated at time delta t times 2. And here you have the time delta t, and here you have the time 0. Okay, and then I can continue this. Delta t 1 over n is the total interval size. Okay, and now times, what's happening? It's not writing. Okay. E minus I delta t h, the final Hamiltonian, so at 1. So I will say t is equals to 1, and this is kind of this temporal time as we go from 0 until 1, as we are propagating when we are solving the equation on the way, right? So now my psi tilde of 1 will be this unitary u1 at psi 0. Okay. So basically I have two operators. There's one thing that I should still explain. I'm applying to my psi 0, I'm applying u1, and basically psi 0 I should first propagate with this evolution here. So actually I need to put a plus here and then put a Hermitian conjugate, and then this equation checks out. But now if I will spell it out in good order, I have my n times delta t Hamiltonian, I have the same duration, the n minus 1 times delta t Hamiltonian. This tells you at which moment do you evaluate the Hamiltonian, yeah? And then dot 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 e2 minus I delta t h delta t e2 minus I delta t h0 applied to psi of 0. Okay, so I will skip one step. So h0 applied to psi of 0. Okay, so this is kind of natural, and you see if I have a piecewise constant switching of my Hamiltonian. So for example, I have a Hamiltonian which looks, for example, like this. ht is a plus Heaviside delta of t minus t0 b, right? So I would have a single kick and switching the Hamiltonian to h plus b after t0, and before t0 I would have only a, right? I could have many such kicks, and this is how you can view this kind of evolution. So in general, if I do it for many such small changes of the Hamiltonian, my total solution to the Schrödinger equation I can write down, because it's a composition of small evolutions with this updated Hamiltonian. Okay, I see something in chat. I have a question about quadratic Hamiltonians. This is any matrix d by d. So we are not restricting here to a Gaussian evolution. So this is in the full Hilbert space. Is quadratic Hamiltonian linear? Well, any Hamiltonian is always linear in Hilbert space, as defined by the corresponding Schrödinger equation. Okay. The dependence on time can be very nonlinear. This is fine, right? But at any given time, yeah, we are working in Hilbert space. Similar formalism holds for Gaussian systems. This is a good comment, of course. But there we would be deriving as something similar in mode space, and it would be a similar mathematical question actually, whether you work in the mode space of a Gaussian system or whether you work in Hilbert space. But in this case, we are working in Hilbert space, and we just have a dimension d, right? So we basically have a d-dimensional matrix. This d could be 2 to power l in the case of l qubits, but it can be any dimension. And then this Hamiltonian might have solvable dynamics or might not, but we are just considering the problem of how small do we need to make this delta t so that this piecewise constant evolution here will approximate our evolution. So this is my psi of 1, is this. In general, we can write psi of t, but depending on, don't know if this is actually helping or maybe distracting. But I have also the full solution at the final time of our evolution, which we are setting to 1. And we are asking what was the dependence here on delta t? Can we derive, for example, O of delta t, and what will be the constants? Okay, so a reminder from previous tutorials, if I write this, then it means that there exists some constant such that I have this kind of scaling. And I could be interested, for example, in this dependence on the constant, on some properties of the Hamiltonian. So for example, one idea is that we would like to have some dependence on the derivative. And here we would need some supremum of t in our interval. That's why 0, 1. Okay. And that's what we did. What we said is h prime, and this is smaller than infinity. We kind of assume that kind of stuff. Other than that, if the Hamiltonian changes are smooth enough, then it's fine. This kind of stepwise kick is fine, but yeah, should be kind of decent enough. Yeah. So this is our problem. for any time-dependent Hamiltonian evolution, can we bound it and understand what's going on? Okay. So one geometrical thing how to interpret this is that, for example, for d equals 2, we have a qubit and we have the block sphere here, right? In general, what you have is that if you fix h, or let me use a, I fix a in our Hermitian operators, C d by d. D by d here, then e to I t a will be a geodesic. So for all t, this is a unitary matrix. I think we were using also the notation d-dimensional unitary matrices, and this will be a geodesic curve. Which means, given a notion of distance that I will not be defining, it's the shortest curve, shortest continuous function, starting at I0a, which is the identity. So starting from the North Pole and reaching e to IA, which is maybe some unitary somewhere here, or it could be a unitary somewhere here, depending what A is. So A is a velocity on that sphere here. This is literally what's going on. And this is at all times, this is the tangent to that curve. And at some point, it will bring us to a point which we call E to IA on that sphere. Okay. So now what's going on is that if I have a time-dependent Hamiltonian, I have my block sphere again, okay? And now I have a time-dependent Hamiltonian, which means it gives me some evolution, which brings me somewhere here. And that gives me this point here is our u of 1, for example. At this time, it's our u tilde of t, okay? But we want to approximate this u tilde 1, which is the solution to the Schrödinger equation driven by this time-dependent Hamiltonian HT. Okay, and what's going on is that we will be saying that we are approximating this curve. I will take the ruler, and we want to say that we want to approximate it by piecewise constant evolutions, like that. Okay, and basically each fragment here is E, oops, this I don't want, okay. It's E to I H K times delta T with a minus maybe, right? Maybe minus there as well. And so you see, whenever I fix the interval and then the duration here is delta T, this means that for the duration delta T, starting from this point in that manifold, I considered a geodesic going in that direction for delta T. Then it brings me here, and here I will use E to I H K plus 1 delta T, and the duration here will be delta T again, right? So basically we are using somehow those geodesics. That's the interpretation geometrically of the physics, that basically if the Hamiltonian changes are smooth enough, it doesn't matter if we kind of consider this piecewise constant discretization. And one thing to note, if you have this piecewise constant discretization, so you have H, let's say K times delta T, like this, acting on psi of K minus 1 delta T, then you know what is psi of K times delta T, which is exactly E to minus I delta T HK delta T in this kind of piecewise constant approximation. So what I wrote here is a recursive evolution, and that corresponds to this piecewise constant choices of those geodesics here. Okay, and if we go up, then what I wrote here is the unfolded geodesic equation, right? Because if I would apply this, if I would apply e to minus I delta t h and delta t to psi of n minus 1 delta t, like this, then I would get my psi 1 already, for example, right? So I just spell it out and I bring it to the initial point, the initial condition of the recursion. So we have this recursion here with psi of 0 is our true initial state. Okay. And our problem is to bound those unitaries how they differ, because then for any initial state, the true continuously varying evolution will be maybe at most c times delta t, c times delta t away from each other. Which means if I put delta t towards 0, they become the same. Okay, so that's our goal. Let me check the chat. Okay, no questions so far. Yeah. So wait. Okay. Okay. So if there will be some questions, we can go back to it. So that's basically the idea. With geometrically, if we have a time-dependent Hamiltonian, then it's an erratic movement on top of in general the unitary group manifold. For 2x2 unitary matrices, it's essentially the block sphere. So here it literally looks like my drawing. So a single qubit time-dependent a Hamiltonian or time-dependent control of some superconducting qubit would be doing this kind of erratic curve, while if you keep the Hamiltonian constant, then what you get is basically, it's called the large circle of the sphere or something like this, right? That's why it's the geodesic, because it's the fastest way to bring 2 points. And of course, if instead of that, I would be going like this, then I'm kind of wasting time. I still get there. I can still get there with this time-dependent Hamiltonian, but maybe I kind of wasted a bit of time. Okay, that's the difference. And it's not to say that those time-dependent Hamiltonians are not useful. Okay, it's just they are useful for something else rather than going to some point the fastest way. If you want to go the fastest way, that's why those geodesics pop up. Good. So what's the time? Okay, that's basically the setting. If we hurry up, we can finish this kind of bounding stuff in maybe 15-20 minutes. I can also show you the wrong ways of doing the bounds, and I don't know which way is more didactic, to to first show you the right way of doing this and show you the many ways it can go wrong, or to confuse you for half an hour and then when you're already tired, show you the fast way. I'm not sure. Okay. Let me show you this the fast way. Let's how to okay, we will need some discussion of what happens if I have diverging in the sense differing from each other Hamiltonian evolutions. So we want to consider some perturbation formula. Okay, I'm drawing this in green. Minus I delta t psi of t. Maybe I will write psi 1. is h1 psi of t, psi1. And I have also another evolution, psi2 delta t is equals to h2 psi2 delta t. And I'm forcing them to be the same at the initial time. So what we were deriving using integrals was that we showed that e2 minus t h1 minus e2 I will write t here maybe, t h2. We showed that this is upper bounded by t times the norm difference between h1 and h2, right? Okay. So now what we need to understand is whether we can show that if my t is a small tiny epsilon, it's larger than 0, whether we can bound it uniformly in time. So I will need some tricks. Let's see if we can get some tricks to solve this equation. And we are considering a very small interval. I'm checking my notes if I wrote it nicely somewhere. So what is the evolution h psi2 of epsilon? Norm difference minus psi1 of epsilon. Well, this is solving the Taylor expansion. So this is actually equal to psi2 of 0 minus psi1 of 0. I want to try if I can do it with, because I have like a longer discussion. And then then I have plus some psi maybe, or here we actually put the epsilon. We will have some Lagrange term or whatever. All those things will be very small and bounded by epsilon. So I will have here dt of psi2 evaluated, I think, in the Lagrange point as well here. And then minus also the derivative acting on psi1, right? Psi. So what I'm using here is with equality f of x is equal to f0, plus there's some appropriate way of saying there's some psi x, f prime psi x, and psi x will be this Lagrange point between the expansion point and the final point x, right? I don't remember exactly what's the name of those things, right? But because I was forcing the initial condition to be equal, I get that this is basically upper bounded by epsilon here, and then the supremum over t in 0 until epsilon of dt psi2 epsilon minus dt psi1 of our psi here. And psi I drop because I take the psi in particular will be lower, smaller or equal than this evaluated at the supremum. I might get unlucky, it will be the supremum, but it might also be upper bounded here. So what do we get? We get smaller or equal than epsilon, this supremum here over t in 0 and epsilon. This epsilon makes this interval quite short. And then I will have here the Schrödinger equation. Here I will have H2 applied to psi2 of t. And here I will have H1 applied to psi1 of t in that interval. Yeah, so this is actually where we run into problems, and we can try to solve this equation in some way. But you see that it becomes quite recursive. So what used to be the evolution is kind of bounding this at all previous times. So what is the maximum of that difference? It's basically, I think what we can now, I need to think whether we can do it that way, t in 0 and epsilon, and then consider h2 minus h1 applied to psi2 of t, minus h1 applied to psi1 of t minus psi2 of t. So that will give me a recursion, and this recursion is actually not particularly helpful because we will get our norm difference here. This is nice. So I can enter here with the triangle inequality, and the problem is this term. Okay, so we need to do something smarter, and now I need to think what was the better way to do it. But basically the idea is to have a perturbation formula that allows us to say that that those changes in the Hamiltonian are not differing too much, that they cannot be too far away from each other. Okay, so let's see. Okay. So I had I think I didn't bring the notes how exactly that was going. But basically, we need to be able to show that that for a small interval we have this perturbation formula that that the two evolutions generated will be smaller than epsilon h supremum in this small interval t in 0 until epsilon. If we have this, then in that small interval we are in gain. And then basically we can say that the continuous evolution is chopped into smaller pieces, smaller time intervals, where sometimes you are so in each interval you do this continuous evolution, so you just compose this seamlessly, just the continuous evolution goes that way, and then you compare starting from this point to that point, how much does it differ. Okay, so if I have my full evolution from 0 until moment 1, the full continuous evolution with this continuously changing time-dependent Hamiltonian, minus U1 discretized on endpoints. So when we have that, when we have this result here, it makes everything much simpler, because what's going on is that we can start comparing those evolutions at different moments. So I can start doing telescoping, where I will consider the evolution, the continuous evolution until the moment 1 minus delta t, and then I have the evolution from 1 minus delta t until 1, right? It's just concatenating the Schrödinger equation. That's just the unitary evolution that we have. And then here I have u, let's say, I don't know, e to minus I delta t h0 until e to minus I delta t h n minus 1, n times delta t minus 1 times e to I minus I delta t h n. Okay, there's the norm there. Sorry about this. And now the thing is that we in each interval the difference should be quite small, because the Hamiltonian shouldn't be changing too much in the interval. And then even though it's time dependent, using this kind of uniform upper bound, if we have it in hand, we can kind of recursively go down. So basically what I will take is this u1 minus delta t operator. I will keep from 1 minus delta t until 1. And then I will add and subtract u minus delta t e to minus I delta t h n, my last evolution here. I add it into place again, minus delta t e to minus I delta t h n. I just add and subtract this. And here I will have the plus u n t. So this term goes here. And then we use the triangle inequalities to say that this is this. And that becomes nice because by norm invariance, we can forget this, and this will become 1. So in that interval, we get this maximum bound. So we will get delta t times h prime. And here we kind of lower the problem of discretizing this interval and approximating it with this evolution. So basically at the end, using this thing here, we will get something like n times, there should be some epsilon squared. So maybe n times delta t h prime. And if we do it correctly, I should get delta t squared. So that's something that I'm trying to find. So that wasn't on purpose showing you how the bound doesn't work, but kind of trying to derive this on the go, because I didn't bring the piece of paper where I thought I had the proof. Okay, so I need two things. I need to know how exactly to use this bound on small intervals. And then basically in each small interval, my evolution, which we could designate as u1 to be this kind of time ordered notation dt h of t, which we want to prove that this is limit of n going to infinity of e, in this case, e to minus I delta t h maybe n until e to minus I delta t h0. Okay, so we are trying to prove this because this becomes our un evolving until 1. We have n or n plus 1 discretization steps. We have our delta t, which on the interval from 0 and 1 is 1 over n. Okay, and that will play the role of the epsilon in the small steps. That's what we would like to have, because then you see that we can chop this up into this kind of notation. 1 minus delta t dt ht, then times e to minus I 1 minus 2 delta t 1 minus delta t dt ht until e from 0 until delta t ht. Okay, so that's our full evolution, which is just trivially composing the symbolic integral operators, and each one is defined by giving you the solution to the Schrödinger equation on the interval from t0 until t1 or something like this, right? On each of those small intervals, this is the solution of the Schrödinger equation because it's a linear ODE. It doesn't depend what we are evolving. It's always the same operator. Okay, so there exists this operator because it's the solution to the Schrödinger equation, but it's a time-dependent generator, right? So now we want to do this kind of approximation. And the simplest way would be to say that this is just the Euler scheme for the time-dependent Schrödinger equation applied to a vector psi0. So psi0 is some vector in our finite dimensional Hilbert space C2⁻d. So we have this ordinary differential equation here, I dt psi0. And because an evolution and because a solution exists, we just say that we have this, you know, we could say the Euler scheme converges or something like this. But now we are trying to prove this with those unitary properties just as an exercise to see whether we can get it. Yeah. So if I would be using a theory of ordinary differential equations, I don't need to be proving all those things. But you could say, I mean, you can argue whether it's constructive or not constructive. One thing why this notation is nice is that it's explicitly constructive. It gives you both the discretization schemes and kind of the limit point of the final unitary. Okay. So let me see if I'm making sense. There's no questions in the chat. But anyway, so there are two steps. Once I have this decomposition into those true continuous evolutions in each step, if I am able to show that e to minus I t0 until t dt h t is approximately minus e I t minus t0 no, t0 to t1, let's say t1 minus t0 h of t0. If I can show that this is smaller or equal than delta t ht, then we are more or less done, almost done, right? So we need some sort of uniform bound on that. So and the trick is that on a small interval, I think we can apply some bounds that normally we would be worried about. Okay, I think I was doing this with some sort of integral. So integrating dt so there should be some t here. Psi t is our t prime, let's say t0 until t is our psi of time, right? So so basically on a small interval, I can compare the solution to the piecewise constant approximation at the initial point with this. So psi of t, I think this will work now, minus e to I t1 minus t0 h t0 psi 0. So this is integrating dt prime from t0 until t1. Here I have this t1 here. From t0 until t1. The Schrödinger equation here, psi of t prime. Minus the same thing here, but this will be just ht0 on psi 0. And then I can upper bound this by taking out the integral from t0 until t1. And let's see if we can if we can bound this like this. And the point is that using the Schrödinger equation, I will have ht here. There will be some I. Psi of t prime minus ht0 of psi 0. And for some reason, it's again recursive. I'm doing something wrong. Yeah, so I'm actually showing the wrong way. Another proof idea I had is a bit more complicated, and I don't know, maybe somebody sees it in the chat. I don't know if you guys have an idea. Because the problem is that I was trying to prove the difference of psi t from the constant evolved, but I'm getting this continuous thing here. And I'm not able to, I would like to reduce this to just the integral of dt, and then ht minus h0, which everywhere differs by a small amount if it's t0, t1. But because of this, it becomes recursive. So so maybe we use that this is a differentiable function psi t, and maybe we Taylor expand here around psi around 0. So what would that be? I have ht integrating this dt from t0 to t1. ht and then psi of 0. This is a good thing to have. Plus dt d psi of d psi times times some epsilon or psi. So basically, we say that here, maybe using the Schrödinger equation. And what will I get? I will get smaller or equal dt t0 t1 ht minus ht0. This is good. Times norm of psi 0, which is 1, plus xi d xi h xi. So this is not too bad. So we get epsilon, the supremum of ht minus ht0, plus something like epsilon squared, and then this h prime constant, the supremum over the derivatives. So I'm removing the integral by replacing by supremums, and we have the norm here, right? So this is quite good. And the supremum here I could multiply in psi, and then I have supremum of ht minus ht0 divided by epsilon plus epsilon squared h prime. And if I would do it more carefully, I would get epsilon squared times 52, whatever. I mean, I would need to link this finite difference quotient to h prime, but this can be done. Okay. So we have the correct scaling in epsilon, and we are relating this to the changes in the Hamiltonian over time. So if the Hamiltonian is changing rapidly like this, then our piecewise constant approximations won't be keeping up very well until we are resolving the biggest change in the Hamiltonian, because sometimes we would be slicing through those changes like this and we don't even see those spikes, and that might be important. Okay, so what do we have here? We have that the difference of a short duration evolution, so T1 minus T0 is some small epsilon. The difference of propagating with the time-dependent evolution, our Hamiltonian, and just taking whatever that Hamiltonian was in the beginning and evolving to that duration, total duration. So basically, instead of doing something like this, you take the constant approximation starting at ht0. So this moment here is T0, this is T1, and we consider this for epsilon. And because epsilon is small, this kind of change in the Hamiltonian delta HT doesn't matter so much. Okay, then I inserted the integral here, just rephrasing psi t as an integral. And I do this so that I can nicely obtain here the time-dependent Hamiltonian HT prime, right? And the problem was that this was kind of recursive, so we added here again this f of x is f of 0 plus psi x f prime of psi x. It doesn't matter that those are matrices. This is the same Taylor expansion. It's just I didn't check it on Wikipedia if this is the Lagrange error term, I think it's called. Right? That should be fine. And then what we have is that we are expanding there. I still need to put in that here in. And the nice thing is that psi 0 and psi 0 they agree, so I can basically say this is 1, and then I get the norm difference of those Hamiltonians in that interval. And the Lagrange term, if I integrate this over psi t here, I can consider the maximum derivative, which we denoted by some number h prime. And then I will get from psi t, I can always upper bound psi t by epsilon, because psi t is going from 0 or T1 to T2, so it's all good, right? And the integration of dt times 1 is given by epsilon. So I get this epsilon squared, that's actually important here. And we have this finite quotient here because I can multiply in an epsilon, and I get here an approximation to the derivative. I could again use Taylor expansion, but now for h of t if the derivative exists. So t0 plus psi t h prime psi t. Right? And then because I'm doing the supremum, it's all nicely canceling, and then we are more or less in game with all those expansions. I think that will be working well. Yeah, I think this should be fine. Right? So what am I missing in that calculation? Once I use this, if I have my supremum, ht minus ht0 divided by epsilon, I have that this is psi t h psi t. I'm taking the supremum of t and t0 until t1. It's maybe better to set t0 to 0 for all those f of 0 expansions. Epsilon here. But this is smaller or equal than taking epsilon, and then supremum here over t h, and I can relabel the psi t variable and psi, because psi t is always smaller or equal to epsilon. So we get a nice bound here. Okay, which means that now if I have this evolution, for all those constant, piecewise constant evolutions, I get that u from t0 until t1 minus e to minus I delta th of t0 is smaller or equal delta t norm of dt ht0 and supremum t from t0 until t1, right? So I get this, and now we are going back to what we were discussing for Trotter-Suzuki formula, because I could basically write u until 1 minus our approximation u evolved to n. We can do this by writing this as piecewise product. Okay, this is not working.